Hi guys, and welcome to this video on approximation and rounding to decimal places. It couldn't be more exciting. My name's Darren. Welcome. Really good to see you. If you are new to my channel, do me a favor and subscribe. Greatly appreciated if you could. Never going to be rich and definitely never going to be famous. And there's also MaffsGuru.com, which is my website, which you can watch these videos. They're ordered by textbook. What else can you do? Download lesson notes, exam questions, and all sorts of stuff over there for you. It's absolutely free to sign up, so head over there if you can. Whoa, seems like we're going to do a lot of maths today. But again, a lot of this is building on the stuff you've already done. It's more sort of the foundational stuff that's going to be used for the rest of this course. And this stuff is freaking funky. We need to know about rounding numbers, scientific notation, significant figures. There's so much, let's just get onto it. Now, in previous lessons, we've looked at BIDMAS, we've looked at directed numbers, and the very last video was powers and roots. Again, if you haven't watched those videos, maybe head back. They're all on YouTube and MaffsGuru.com. And then we're going to build, all right? So orders of operation, BIDMAS, making sure we do things in the right order. Powers and roots, what is a square number, a cube number, what is a cube root? And directed numbers about adding and subtracting. Now negatives, funny enough, throw people. So head back there, make sure you know about the 4 rules because they're going to come in handy. Rounding numbers, why on earth would we need to round numbers? Now there we go, is my very good friend Usain Bolt. Actually, I have no idea, I never met the guy and really don't watch much sports, as you probably can tell because I'm stuck in this room talking to myself all day. But Usain Bolt, there are his personal bests. I don't know quite what he's good at, no idea, it's running. But what we'll notice is we see that the world record for the 100 meters was 9.58. Hours? That seems like a long time. No, I know, it's seconds. 9.58 seconds. But the thing is, was it 9.58 seconds? Probably not. That figure there has been rounded to 2 decimal places, right? So 9.58. There is my decimal point. There is 1 decimal place, and there is 2 decimal places. So there are 2 numbers after the decimal place, and it's been rounded. But was that his real time? Honestly, probably not. Why? Well, we can actually round. We can measure time to some crazy number of decimal places. So his actual time, as I say here, might have been 9.57938721. Anyway, it goes on. The point of it is we're not going to want to measure his time that accurately. It may well be that we really only wanted to know what his time was to the nearest whole second, in which case we'd probably say 10 seconds. How did I know that? It's coming up. But rounding decimals is actually really important when we want to try and not give the whole number, but something that's close to it, an approximation. And again, this 9.58 is approximately what he got. It wasn't exactly what he got because we've taken and we've ignored all those other decimal places. So when we round numbers to certain numbers of decimal places, that's actually quite funky. There are 4 rules. Now, they're slightly different from what other people use. So let's have a look at the number 9.58974336, for example. So the first thing to notice is our decimal point. Now, I think of things as the chosen number and the almost loved numbers. What does that mean? Well, for example, if I want to round to 2 decimal places, so I want to round to 2 decimal places, the first thing I need to work out is where is that number, all right? Well, here is the first decimal place and here is the second decimal place. So I now think of the number 8 as the chosen one, all right? That loved child that we really, really want. The number after it is the almost loved, right? Not quite. Oh, if they'd only been that one place over in the queue, they'd have got it. So I now have this one here as my chosen and this one here as my almost loved. Now what I say is, look at the value of the almost loved number to the right of the chosen number. Okay, it's a 9. If the value of the almost loved number is a 5, a 6, a 7, 8, or a 9, then the chosen one goes up by 1. So because this number here is a 9, then I'm going to increase my chosen number by 1. So that becomes a 9. If the value of the almost loved number is 0, 1, 2, 3, or 4, the chosen number stays as it is. So we don't actually, so we either choose rule 2 or rule 3. We can't have both of them. And rule 4, the almost loved number and all the numbers to the right become nothing. So that 9 becomes a 0, 0, 0, 0, 0. All right, so they all effectively become zeros. I'll come back to that in a moment. But what about the numbers on this side of the chosen number? Well, they stay, for this particular example, exactly the same. So 9.59, whoa. But you remember when you were at school, what did we say about decimals and all those zeros at the end of decimal numbers? They actually disappear. We don't have to write them. And so we now can see that that number there has been rounded to 2 decimal places because there are now 2 numbers after my decimal point. Let's round this number to 2 decimal places. It's close to the one we've got, but let's just check. So we've got 9.57938. It goes on, but because it wants it to 2 decimal places, which one of these numbers is my second decimal place? Well, here is my decimal point. Here is the first number. So there is my chosen number. Here is my almost love number. Ask yourself the question, is it a 5, a 6, a 7, an 8, or a 9? Yes, it is. So it means that this number here, we add 1 to. So that becomes an 8. All the numbers on that side become exactly the same as they were. So that's 5, point, and then the 9. And all the other numbers become zeros. And we remember that we don't actually need to write those zeros. And there we go. We have now got Usain Bolt's 2 decimal place time, 9.58. Let's round it to 4 decimal places. 9.5793872. So where is my 4th decimal place? 1, 2, 3. There we go. There is my chosen number. There is my almost loved number. So it's an 8. Does that mean that the chosen number goes up by 1 or stays the same? Congratulations, it goes up by 1. So that 3 now becomes a 4. That stays as a 9, 7, 5, point, and 9. All of these other numbers become zeros, and after a while you won't even need to write the zeros simply because we know they disappear. But again, be careful because that is for decimal numbers only. Sorry, phased out for a moment there. Okay, now because I've rounded this number, generally speaking, I always write 4 DP in brackets. That tells your examiner or the person marking your work that you have rounded it, that it is an approximation. What about rounding numbers without decimal places? Well, actually, funnily enough, the same idea holds true. There are still chosen numbers, there are still love numbers, but as there are no decimals, we need to be careful with the zeros. So, can we round 35,785 to the nearest 1,000? Well, first things is, we need to know about our place value. So if you remember, this is our units, this is our tens, my hundreds, and my thousands. So we want the nearest 1,000, so that 5 now becomes my chosen number. And as usual, we look at, the almost love number, which is a 7. Now, does the 7 change to 5? Of course it does, because a 5, 6, 7, 8, or 9 means that it goes up by 1, so that 5 becomes a 6, the 3 stays as it is, and all the other numbers become zeros. And this is where lots of people now get tricked, because they go, oh, it's okay, because I can get rid of that. No, you can't, because how is 35,785 close to 36? It isn't, all right? It is close to 36,000. Because there's no decimal point here, I can't get rid of it. If there were other numbers here that then became zeros, then yes, I can get rid of all the zeros after a decimal point because we know that that is able to be done in maths, one of those rules. But there we are, we can now round to the nearest 1,000. Now we get to scientific notation. I love scientific notation. It's all about jumping decimals, about how to jump a decimal point. So we're going to go back to a previous video on powers, and what do we notice here? Well, we know that when we have long lists of the same number multiplied by itself, we can write that in index notation or power form or whatever we need. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 10 to the power of 12. That's what that means. That 12 tells me I've got 12 lots of the 10, but with kisses in between them, or timeses. All right, now how is that important to me? Well, we can use this funky fact to change how numbers look. Again, it's the same number, it just looks differently. All numbers can be written in scientific notation. All right, so I'm going to show you how to do it, and then we'll talk about the rules. So I now know that 34 is exactly the same as 3.4 times 10. Okay, makes sense? I know that 750 is equal to 7.5 times 10 times 10. Now, how is that the case? Well, at the moment, where is my decimal point for the 750? It's at the end. If I bounce it back 2 places to sit between the first 2 non-zero numbers, hold on a moment, I've given you one of the rules, then I would have to make sure that I multiplied it by 10 and 10 again to bounce the decimal back to where it wanted to. But hold on a moment, we just said that where we have a lot of repeating tens that are connected by timeses, we can write it in a different way. So that becomes 7.5 times 10 to the floaty 2. What about 47294? Well, the decimal point is here. It bounces 1, 2, 3, 4 places to get to the front of that number, or between the first two numbers. 4.7294 times 10 times 10 times 10 times 10. Now, if you don't believe me, put that into your calculator and you will get back to 47,294. But again, we know that we can write this as times 10 to the power of 4, because we've got 10 times 10 times 10 times 10. Okie dokie. So what is scientific notation? Well, I'm going to put a little floaty 1 there. That is scientific notation. That is scientific notation. And that is scientific notation. Now, scientific notation, always, the numbers have to be expressed with a times 10. That's what scientific notation is. There's always a number here. It can be positive or negative. We'll come back to that in a moment. And there is always a number here. Now, this number here has to have a decimal point between the first two non-zero numbers. Okay, now that's the trick here. If you noticed, I moved it between the 3 and the 4 because they were the first two non-zero numbers. 7.50 because it was the first two non-zero numbers. 4.7294 because the first two numbers that didn't have a zero in them were 4.7. And again, that's a stupid rule because it changes. We can do it with decimal places as well. So again, I've got 4.3. The decimal place is already there, but is it between the first two non-zero numbers? No. So I now need to move it one place. So that makes it 3.43, but times 10 to move the decimal place back to where it wanted to. What about 735.72? Well, again, how many places do I have to jump it to get it to between the first two non-zero numbers? 7.3572. I'm moving it 2 places, so times 10 times 10, which we know is 7.3572 times 10 with a floaty 2. There's a floaty 1, and 4729.403. How does it bounce? 3 places, absolutely. 4.729403 times 10 times 10 times 10 to make sure those 3 places, which gives me 4.729403 times 10 to the power of 3. And again, do you notice how many places did the decimal point move with that one there? 1. What do we notice about the floating number? It's a 1. How many decimal places did we move here? 2. What do we notice about the floating number? It's a 2. And how many did we move here? 3. And what did we notice? 3. So now I've got a shortcut, if you will, to allow me to go straight to this without this additional line of working. So really, it's just about bouncing decimals. Bouncy castles. I love bouncy castles. Too old for them now, but anyway, they tend to pop when I get on them. Anyway, whole new discussion. So if I have the number 47.392, I can now go straight to scientific notation. I'm going to move the decimal point to between the first two non-zero numbers. How many places did I move it? I moved it just once, and there we go. Now, if the decimal point moves that way, we have a positive power, right? So you'll notice that this one here is +1. If I have 0.00392, for example, now where is my decimal point? It's here. I need to move it between my first two non-zero numbers. Well, that means I've got to move it to between the 3.92, all right? Times 10. Now, I'm moving it 1, 2, 3 places. I'm bouncing it over 1, 2, 3 numbers. So it's definitely going to have a floaty 3. But when I move the decimal point that way, I must make the number negative to show that we've moved it the other way. Now, there's a lot more behind this, but it's probably slightly beyond the scope of this video. But we must make sure that we look at our bouncing decimals. So here are some examples. 7,800,000. Right, where's the decimal point at the moment? It's at the end. So it's going to bounce 1, 2, 3, 4, 5, 6 places to give me 7.8 times 10 to the power of 6. And because we're moving it that way, the 6 is positive. What about 0.00000005? Well, in this situation, now, bit of a trick here. Where am I going to move the decimal point to? The first two non-zero numbers, but there's only one 5. But we remember with decimal numbers, we can put zeros on the end without changing the size of the number. So that means it's going to bounce 1, 2, 3, 4, 5, 6, 7 places. So we get 5.0 times 10 to the minus 7, because when I move the decimal point that way, it becomes a negative. Let's have another example. What about if I had the number 0.000308? Now this is where I don't quite like the ruling here that says, you know, it's about finding the number to the nearest, the first two non-zero numbers. Basically, it's got to be the first number cannot be a 0. That's what I'm effectively saying here. So I can't move the decimal point here because that means the number would start with a 0. I can move the number here because that 3 basically means I can start counting. Now you're going to say, hold on, but you said the first two non-zero numbers and that's a 0 there. And that's why I don't like the rule, because the first number basically can't be a 0. So you're going to move it to make sure the first number is not a 0. So it's going to go 1, 2, 3 places. I get 3.08 times 10 to the minus 3. Why is it minus 3? Because we're moving to the right. Now, what we do forwards, we must be able to do backwards. And so when we are given numbers in standard form, we should always be able to backtrack them as well. So there's lots of ways of doing this. We can think of this as 3.576. Now, we know 10 to the power of 7 is 10 times 10 times 10 times 10 times 10 times 10, 1, 2, 3, 4, 5, 6 times 10. And that means we're going to bounce that decimal place 7 times. 3.576. So 1, 2, 3, 4, 5, 6, 7. And I always say, what's there? And lots of you go, nothing. And I go, congratulations, there's nothing there, nothing there, nothing there, and nothing there. So that decimal point no longer exists there. And there, ladies and gentlemen, is my final answer. 35,760,000. Yes? So that's bouncing it. The other way of thinking of it is just straight from that 7. Yes? Originally, it's moved positive, so it moves to the left, which means I've got to bounce it to the right to undo it. So when I'm reversing it, we undo it. What about this one? Negative. Well, the negative value meant that the decimal point had moved that way. So I now need to undo it by moving it that way. So I've got 7.9, I've got minus 5, so I'm going to bounce it 1, 2, 3, 4, 5 places. There's my decimal point. What's here? Nothing, 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 nothing. And that decimal point is no longer there. Now, this is a bone of contention of mine, a little bit of an annoyance, but a lot of people will now write their number as 0.000079. I don't think that makes any sense. As an examiner, I'm not looking for a number to start with a point. I'm looking for it to start with a 0 point. I don't know anywhere in life where we just have a point in front of a number and we leave it that way. Significant figures are basically just some sort of funky way. Now, remember we had decimal places. So I had like 32.947, and that was my first decimal place. That was my second, and that was my third. Well, basically, same idea, but with significant figures. And so there are rules. So all non-zero digits are significant. So basically what it's saying is the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9 are significant. Thank you very much. All zeros between significant digits are significant, and I'll explain what that means in a moment. And after a decimal point, all zeros to the right of the non-zero digits are significant. That's the one that tends to throw me. Okay, so what we're saying is if I had the number 473920, this has, wow, right, all non-zero numbers are significant. So basically this here is my first significant figure. This is my second significant figure, my third, my fourth, my fifth, and that actually is my sixth significant figure. Why? Because it says basically all not zeros between significant figures are significant. And so once we started counting with 1, 2, 3, 4, 5, that is significant. Even if I had a 0.0 here, that is still significant. All that tells me is I've rounded to 1 decimal place or 7 significant figures. If I have the number 0.0034, for example, this value here is not significant. I can only start counting my significant figures when I get to my first non-zero value. After that, all numbers are significant. So that would actually be my first significant figure. Let's move that arrow so that it's underneath. This here would be my first significant figure, my second significant figure, and they count on. So you're looking for that first number that's not zero, and from then on, off we go. Now, this little table has been taken from the Cambridge General Maths Units 1 and 2 book, and I think it's great. It just gives examples of how these things work. So, if we look at each of the numbers, 596.36, how many significant figures are there? There are 5, okay? Now, what gets me here is this number. So 5123. It says there is 1 significant figure. Yes, that's the one that throws me. So let's just check. All non-zero digits are significant. So there's a significant figure. All zeros between significant digits are significant. So all zeros between significant figures are significant. Now again, to me, that would make the zero significant. Rule 3, after a decimal point, there's no decimal point. Now, the explanation here says there's only 1 significant figure because we do not know anything for certain about the hundreds, the tens, or the units place. The zeros may just be placeholders, or they may have been rounded off to give this value. Okay, so 5,000 has been rounded to 1 significant figure. So I think that's what they're trying to say. We don't know what that number was before, and so theoretically speaking, there is 1 significant figure there because, absolutely, it could have been rounded. All the other numbers to me make perfect sense. So 0.0057, 2 significant figures because the 5 and the 7. Even 560.0, it says there are 4 significant figures there, 1, 2, 3, 4, and it says the 0 in the 10th place means the measurement was made accurate to the 10th place, and the first 0 is between significant digits and is therefore significant. So this stuff, I would just go and sort of cut this out, put it in your summary book and just check. The one that tricks me all the time, I suppose, is that one there. Here are examples. Right, let's round this number to 2 significant figures. So we can do this in the same way as we do with decimal places. We have 93.738, 0, 9, and 5 to 2 significant figures. So the question is, where is my second significant figure? Well, this one here is my first, that's my second, and so that now becomes the chosen number. And this one now becomes the almost loved. Same process. So is this number a 5, 6, 7, 8, or 9? It is. So the 3 becomes 1 higher. The 9 stays as it is. And the rest of the numbers all become zeros. Now, because we've got a decimal point here, it means I can actually remove all of those decimal values and life is good. What about if we round it to 1 significant figure? Okay, well, here is my first significant figure. Here is my almost loved. Does the 3 change the 9? No, it doesn't. So the 9 stays as it is. All the rest of the numbers become zeros. And in this situation, they can go because they're after that decimal point. And 5 significant figures, 93.738, 0, 9, 5, 1, 2, 3, 4. Here is my 5th significant figure. There is my almost loved. Oh, sorry, that's my chosen one. There is my almost loved. Does the 0 change the 8? No, it doesn't. So 8, 3, 7.39, and all of those become zeros, which after the decimal place, as far as I'm concerned, disappear. We can do the same with decimal numbers. 0.006473, 4 significant figures. Now remember, the first significant figure can't be a 0, so we start counting here. 1, 2, 3, 4 significant figures. Actually, oh, I forgot the 5. There is a 5 there as well. So now we say, well, there's my chosen number. There is my unloved number, or almost loved number. Does the 5 change the 3? Of course it does. That becomes a 4, 7, 4, 6, 0, 0.0. That 5 would become a 0, but because it's after the decimal point, I'm going to get rid of it. 3 significant figures, 0.006, 4, 7, 3, and 5. So what do we want? To 3 significant figures? 1, 2, 3. That is my chosen number. There is my almost loved. Does the 3 change to 7? Nope. So that's 74600.0. The other numbers become zeros, but they're after a decimal point. And one significant figure, again, 0.00647335. Here is my chosen number. Here is my almost loved. Does that change to 6? No. And in which case that stays as a 600.0. As far as I'm concerned, that is significant figures. Very similar to decimal places. And we're at the end of the lesson. Yay! Okay, it feels like it's been a long one. Hopefully it's been useful. Lots of worked examples. Thank you very much for watching. If you can subscribe to my YouTube channel, that would be greatly appreciated. Head over to MaffsGuru.com and see there as well. Otherwise, maybe I'll see you in another video. If you can spread the word about my channel, I'd be deeply, deeply grateful as well. All right, I'm done. Take care of yourself. Please stay safe in these crazy times. I'll see you again. Bye-bye.